Good afternoon, everyone. Today we are going to learn about dictionaries data structure. Uh, Dictionaries can be implemented using trees and hash tables. So, before going to the discussion of hash tables, let us look why why we need to learn hash tables. Okay. So far, we have discussed searching algorithms like linear search. Searching algorithms like linear search, which takes big O of n complexity for insertion and deletion, and for searching also. Then we have learned binary search algorithm, which gives an searching complexity of log n base 2. So we have successfully reduced our big O of n complexity to log n base 2 by using binary search. Okay. But uh, there is a drawback in binary search that the list should be sorted initially. Okay. So leaving that, can we do the searching problem less in a less time? So is it possible for us to use any data structure which gives us the complexity of big O of 1? Yeah. Let us see what are the data structures that exist so that we can reduce our searching complexity from log n base 2 to big O of 1. Okay. Dictionaries are one of the data structures which allows you to search the data structure with a complexity of big O of 1. Okay. What is dictionaries? Dictionaries are nothing but mapping of unique keys with some values. Okay. Here, you consider an example of direct telephone directory. You can't say that if the telephone directory, if you have seen the telephone directory, you will have the names which are mapped to the telephone numbers. Assume that if you have a telephone directory which you have keys which you have telephone numbers mapped to the name, telephone numbers mapped to the name. Then what? Anybody uses the telephone directory? No, because we are concentrating on unique key thing by keeping the telephone number as a such thing. But it is easy to use a name which is mapped to a telephone number. So this unique key constraint can be relaxed. So if you consider a telephone directory, you may have n number of Venkats, but you need to you can't say that you should have only one Venkat which is mapped to the single phone number. So you can relax this condition of unique keys, and you will learn how much extent can we relax this unique keys condition. Yeah, we can see this. We can see a number of applications of this direct dictionaries data structure. Like dictionaries data structures like language dictionary. You already know these language dictionaries, and symbol table. Symbol table is the one which is used in the designing of compilers, where you need to have the scope variables and all those things. So by the end of this session, you will be looking at the sample implementation of this symbol table. Okay. We will look at different implementation of dictionaries. Dictionaries can be implemented with sequential arrays. In sequential arrays also we can use an ordered, if the data is ordered or unordered, and then we'll learn about the hash tables, then we'll learn about the binary search tree. Okay. Keyless is one of the best implementation for the dictionary. You can learn it on your own. In this section we will discuss mainly on sequential arrays thing, hash table, the binary search tree. Now, if you look here, ordered ordered arrays are best for frequent searches, but they are not good for insertion and deletion, because in insertion and deletion for an ordered array, in a worst case scenario, it will take big O n time. But in any case, searching will be given in big O of 1 for the ordered array. We consider an unordered array. Frequent, frequent insertion and deletion can be done with a constant amount of time, but the thing needs to be done in the worst case to be time complexity will be big of 1. Let us look at how do we implement a dictionary using a associative array. Associative array is nothing but you'll associative array is nothing but you'll map every key is binded to a value. Let us consider this is also known as direct addressing, and let us consider this array, this associative array, as an unordered thing, so that we can guarantee a big O of 1 complexity in for insertion, deletion, and search. For all the 3 operations, we can guarantee of big O of 1 if we consider this as an unordered list. Let us look at this thing. Then we can do all these 3 operations, like, complexity time of big O of 1. Then why do we learn hash tables? Okay, so there should be a problem with this structure. There should be a problem with this structure, so we are learning the hash tables, right? So what is that problem? You consider this array data structure. Arrays are having a main disadvantage that the length of the array should be fixed in advance. Okay, because it is a continuous. We consider a telephone directory as our example. Let us take telephone directory will be having the keys of the people name. So if we consider people name starting with A, we have 30 names. People person's name starting with B, we have consider them as 40 names, 40. And people name similar way, people name starting with Z, we consider as 2. So it might be around, for our case, if you think it might be, assume that it might be around 250 number, 250 size of an array, but we cannot guarantee that all the 250 members that exist will have a telephone number. Okay. Then this array size cannot be fixed in advance. So in that case, if you know the number of people you have, and if you know the number of people in advance, and if you want to create a table of that size, you can't say that the table is fixed with that, and no more people can be allocated, can be kept in the directory. So the size is the main problem that we need to fix in advance. So we need to study a data structure where we can limit our number of slots. Even the input data is not known. We need to fix the number of slots, and we need to able to map all the data that we came across to the fixed number of slots. Let us look how we can do it. Let us suppose consider you have there is a limit on the number of here, as I said in the previous slide, that we need to limit our number of slots. So how can we limit our number of slots? So to limit our number of slots, we need to know the pattern of our data. Consider you are running an educational society. So if you want to maintain your records of the entire students, so an education society will contain its KG students to PG students. You consider maximum age of an PhD student to be 45. Then you can limit your age limit from 5 to 50, 5 to 45. Yeah. This is a universal case, which is a natural number. Ages are natural numbers, right? May contain 0 to infinity. Yeah. Your data will be around your data will be from 5 to 45. You consider as an example. Your data will be in the range of 5 to 45. So you are not need to consider these universal scenarios. You just only consider about the pattern that you recognize the data that is coming to you. You can recognize this pattern of the data that you come across. we can limit this number of slots. You must have a mechanism that you need to map your data to the fixed number of slots. Let us look at some terminology. Here, we have a data like this. Here we have names of people like John Smith, Lisa Smith, like these are nothing but we say them as keys, and we use a function which maps the keys to the number of slots. This function is nothing but hashing. Here you can see that hashing is the main part of the hash table because it maps in n number of set of keys to the limited number of hash tables. So you should concentrate about the hash function that you are choosing. Let us look at what is a perfect hash table, perfect hash function. You are having m keys that need to be mapped to n slots, that is n buckets. With no, your function should be like that. Every bucket should not contain more than m by n. So your hash function should map all the m keys to the n buckets. In any cost, your each bucket should not cross these number of m by n number of keys. Then the function is said to be perfect hash. Okay. So we came to know about what is perfect hash function. So how do we build this perfect hash function? Let us look at some techniques that can be used to build a hash function. Here, before going to the technique, what should be what are the properties that a function should contain if it is said to be a good hash? The function should be easy and fast to compute. Your function is your hash function. If you taken a hash function which is 100% good and does not result in any problem, and your hash function if your hash function takes 10 minutes to compute the hash value, okay, then what is the use of your advantage of your efficiency is going in by the time that is taken by the hash function. So selecting an hash function depends on to be and fast compute the hash value and to distribute the keys uniformly in the table. Let us consider in our section we will consider natural number set as our universal key set. Okay. Now we will learn about different hash techniques. We will learn 4 techniques. There exists more than n number of techniques. Right now we are concentrating on 4 techniques. Truncation is one technique, folding, division, and universal. Let's start with truncation. Truncation is nothing but we ignore some parts of the key and use the remaining part of the key to directly to map the key to the table. Okay. If you take an example of 8-digit number, you take your keys as an 8-digit number, and if you try to map it to the hash table of having a size of 1000 entries, then we'll here we'll take a strategy of I will consider first digit, fourth digit, and the 8th digit to map the key value to the hash table. And let us see the example. Here is the truncation example. Here I have a number like 1, 2, 3, 4, 5, 6, 7, 8. Okay. Based on our previous strategy, we will consider first digit, fourth digit, the 8th digit. After truncating the numbers 2, 3, 4, 5, 6, 7, we get that 148 as a key value that is mapping to this part. Okay. Let us consider another example which have 1, 2, 3, 4, and 5, 7, 7, 8. Okay. Here also, if you truncate 2, 3 and 5, 7, 7, here there is a change in the number, but you are mapping it to the same slot. Similarly, third example is also mapping to the same slot. So, you consider largest number set So which we are considering as a natural number set, it contains from 0 to infinity. We can we can't say that n by m elements are mapping to this 148 because more as the number is more and more numbers are accumulating at 148. More and more numbers are mapping to 148. Let's look at a better technique. It is nothing but folding. Okay. In the folding, what we do is we'll break up the key to parts and combine them in some way. For example, we take the previous example that we have seen earlier, that our keys are 8-digit numbers, and again we are mapping them to hash table of 1000 entries. Now, what I do is break them up into 3 parts. Each part, first part contains 3 digits, second part contains second part also contains 3 digits, and third part contains 2 digits. And I need to combine them in some way. Here I am considering some to combine these values. Okay, let us look at an example. Okay. Here is the folding example. I have taken the same examples as we have discussed in the truncation. I have taken the same number 1, 2, 3, 4, 5, 6, 7. Okay. Here I will take the first, according to our strategy, we will take first 3 digits as 123, second 3 digits as 456, then last 2 digits are 78. Then I will sum up these 3 digits. Okay. Related in red. Then we need to sum up these. It results in 8. So you can place it in 8 slot. Yeah. Let us consider the second example. It resulted in 8. Initial case, when it is in truncation, map it to same slot, that is 148. Now it is mapping to another slot 58. Consider the third example. It is again giving 667, which is already filled by a number of 1, 2, 3, 4, 5, 6, 7, 8. Okay. So there is a problem of again there is a problem of mapping not more number of keys as truncation, but a limited number of keys to the same slot. Yeah. You take maximum number in the 8-digit number, that is all digits with 9. You will get a value that is 2097. Yeah, 999 plus 999 plus 99. It results in 207. So we can't map this to the hash table because we have a slot, maximum slot at 999. So here, then the sum processes the number of slots that are available for us. What we do is we use our truncation technique that we used earlier. That's nothing but I use the first digit and the fourth digit. That is nothing but 27. Yeah. Even then, we have reduced the number of keys that are mapping to a single slot. There exist some numbers like we have seen 1, 2, 3, 4, 5, 6, 7, 8 and 1, 2, 3, 4, 7, 6, 5, 8 are mapping to the same. So let us look at another technique, which is known as division. Here in division, we will use a function which is equal to our key value modulus of our table set. Okay. It is fast to calculate. One advantage is it is fast to calculate, and to see the function here, the main part is played by m, nothing but number of slots, because it is divided. We are taking the modulus of m, right? So m is the main part that needs to be concentrated to make this hash function a good answer. So how do we choose this value m? Yeah, let us concentrate on how do we choose this value. If you choose for suppose you choose the value of m as a multiple of 2, okay, 2 power n, then all the even numbers, then all the if your keys are all even numbers in the worst case, you take a modulus of 2, then you will result in all the key values all the even key values that are that from your data set will be mapped to the position 0 in the 0th slot in the table. Okay. You take your m value as multiples of 3. Let us consider if you take your value, you take your m value as multiples of 3, 3 power n, and so on. Then all the odd numbers, in the worst case, if you have a data set of all the odd numbers, then all the odd numbers will be mapped to the slot 0, because all the odd numbers that are when you take a modulus value of 3 or multiples, let us consider 3, then all the variables are mapped to a slot 0. Okay. So in this case, what is the best thing to choose m value? So we have a numbers like prime numbers. Concept of prime numbers is the number is divisible by one and itself only, and it cannot be divided, and it cannot be divided by any other number. So m should be a value, should be a prime number. It's better to take a prime number, which ensures you the distribution of your keys uniformly in the hash. So one more important thing is you should not take your prime number m such that it is close to any powers of 2. Let us look at this is most of the problems can be eliminated using division technique. Here is the previous example. Uh, by using the division technique, here we have taken the same numbers and we are dividing it by we are taking the modulus by the number of slots. Here you can see that different keys have been. Let us look at some other hash technique. But, universal hash. Till now, we have considered a single hash function, right? So all the keys mapping to the slots are based on the hash function. So in universal hash function, we'll take a collection of hash functions. So taking one hash function, we'll take a collection of hash functions, and we'll select random. We'll select one random hash function from the collection, and we'll perform the hashing. So this will result in a good performance. So instead of universal, so okay, here how can you say that this universal hash collection is good? A taken collection of hash functions. Right? So how can you say that this collection, these number of if you have taken 5 hash functions, then how can you say that this set of 5 is a perfect will result in a good hashing technique? Okay. So to say that, you need to perform a random check by taking distinct elements like K and L along to take pairs like keys like K and L which belongs to the universal set data. And if you take the hash function randomly from the set of collection of hash functions, if you take the hash value, this h of K equal to h of L will happen modulus h by m. It not cross this value. So if it is less than or less than this value, ratio number of hash functions by number of slots, then you can say that hash set that you have taken is a universal hash set. So after rigorous checking, you can make a set like this thing. One more drawback with universal hash function is you need to remember the hash function that you use for a particular key. For every key, you will be selecting a random hash function. So you need to keep track of these mapping that for a particular key, we have used a particular hash function. These mapping should be needs to be remembered in order to search or delete other operations. Okay. Let's look at a scenario of hash table. We'll consider division technique as division technique for mapping the keys to the hash table. Okay. In this scenario, consider you are running a airline. you need to store all the flights that you have, all the flights information that you have. Okay. You have information in the sense you need to have origin, destination, departure time, arrival time, available time. So suppose if you have 99 flights of your airline, okay, then what you will simply do is you create a hash function like demodulation, right? Okay? Because you have 99 flights, so maximum you can have 100 slots, right? Then every flight number will be mapped individually to its respective slot. Here, if you take 12 modulo 10, it will map to its slot. So here you can store the data like origin, distance, path, okay. Let us extend our scenario and look at some other extension of. Let us look at some extension of. You are considering a traffic control system for all the airlines serving in an airport. In the last scenario, we considered our own airlines. So we have a limitation of, we can limit our number of slots by looking at our number of flights. In the next scenario, if you carefully observe, it's a traffic control system of an airport. So, in an airport, more than 10 airlines will be using your airport. So, you can't have the limitation of the number of you can't limit your slot size to 100 here because your airline itself has 100 flights and different airlines will be having different flights their numbers. So, but to have good use of the hash table, your hash table should be a reasonably sized one. So let us look at the scenario of if you have a flight number of 123. Here I use the same 100 slots and I use the same hash function modulo 10. I map 123. What I get is it will map to a slot 23. Here I will keep the information of that. So what is the problem with this thing? You look at this thing, you can see, you look at the problem is here. You can see this hash table. The T123, flight number 123 is mapping to the slot 14 because we are using a prime number for our table size. I have taken a prime number as table size, so 103. So 109. Then flight numbers like 103, 232, and 341 all are mapping to the value table to the slot 14 in my hash table. So here there is a problem of number of keys are mapping to the same slot. So this problem is nothing but collision. Before we go into the problem of before we go into the discussion of collision and about the resolution of the collision, we look at the animation of hash table. So if you consider this hash table, we have 11 slots. Taken 11 slots, so table size of 11. If I want to insert a value like 12, value of 12, we will calculate the hash value is the position is equal to value is nothing but 12 percent 12 because the table size is 12. So it is mapped to the position 0. So at 0 slot, your element is placed. You know, if you are inserting a value 22 to the table, you can see that 22 modulus 12. It results in position 10. So it is mapped to the position. Similarly, you can find so if you have a collision problem here, right, you try to insert 24, value 24 in the table. You see that plot is already filled because it is It is here you can see that 12 by 24 by 12 is mapping to position 0. So already the position 0 is filled with value 12. So it says that slot is already filled. Okay. Now how can you this mapping of elements to the same slot is nothing but collision. And now we'll look at how do we deal with this collision. Collisions can be dealt in two ways. One is known as closed addressing and open addressing. Second one is known as open addressing. Closed addressing is also known as closed addressing is also known as open hashing, or open addressing is also known as closed hashing. Don't confuse with the names. To avoid the confusion, I haven't given the both the names. Just we will concentrate on closed addressing and open addressing. What is meant by closed addressing? Closed addressing, we'll modify the hash table structure so that we can map all the elements mapped to a same slot in that slot itself, but we won't touch other slots that are available. In open addressing, once the slot that is filled, that actually the key that is actually mapped, if it is the slot is filled, then we will check for the other slots available in the table. Let us look at collision based on collision based on closed hashing, closed addressing. Here, closed addressing, we have two techniques like bucketing and separation. In bucketing, we'll divide. So if you look at bucketing, you can divide M slot to B bucket. So that bucket having M by B slot. So every slot we have till now we have considered M slots to map the thing. Closed addressing bucketing, we will divide these M slots into B buckets, and each bucket will be having M by B slot. Okay. The key that maps the first to the slot by hashing will be filled. Then we will check sequentially in that bucket. If you consider values are mapped to bucket number 1, the first mapped element will be first in the bucket 1. If any other elements mapped to that bucket will be sequentially allotted a slot in bucket only. If the bucket is full, then we'll have a overflow bucket, which is an infinite capacity. And then we'll allocate it at the end of the table, so that once the slot bucket has been will be accommodated in overflow bucket. All the buckets all the buckets will share the same overflow bucket. Okay. Then if you are trying to search element, first it will check first slot in the bucket, then it will search in the next slots of the bucket sequentially, and if the element is not available in the bucket, then it will go for the overflow bucket and check sequentially. This implementation of collision resolution, closed address collision resolution bucketing is useful when we implement this table on this, because we just want a single bucket that needs to be searched or that needs to be inserted. Based on our key hash key, we'll only load this required bucket into the main memory. All the other data will be residing on the secondary memory, that is nothing but this. And the memory that we want to insert in the slot, in the bucket we want to insert or delete, search, we'll load that bucket into the main memory. So here there is a disadvantage, because we can't implement a hash table on the disk. Here we need to use a file system again, and we need to use some separators so that we can reconstruct the bucket as we need it. Okay. This is the overhead by using the bucketing technique. Okay. Let us look at bucketing simulation. Let us look at the bucketing situation. Here I will use now three, three slots per bucket, and then I will use my hash table size as 11. Then I will use an overflow size of execute. Here, if you see, each slot has three buckets, and we have a overflow bucket. It has a size of 7, and our hash table is of size of 11 here. You see it. It's, here we are using random numbers to map the values. Let us look at by it step by step manner. Continue. Here we have taken the slot as number of slots per bucket as 2. Slot number 6 is already filled. You get a value which is mapping to 6, then it will place it in the overflow bin. Okay. Let us look at 3, then it is mapped to 0. Then slot 3 is also filled. Slot 7 is filled, slot 4 is filled. Now, here if you look at it, the value 699 modulus 11 mapped to slot 6. Since slot 6 is already filled, what it do is it will fill it in, it will keep the value 699 in overflow direction. Overflow. Okay. Yeah. In similar way, you can see that element now it is mapped again to 6. 281 is again mapped. 281 is again mapped to 6. The slot is already filled, and it will go for overflow bucket. We will check the first slot, it's already filled. So it will keep in the slot number 1 of the overflow bucket. You can see it is also mapping the addresses of where it has kept. So for 6, it has kept in slot number 0 of overflow bucket. Okay. Then you go for the 8th slot. Okay. 327 is mapping to 8. 8 is already filled. So it sequentially searches for empty slot in the overflow bucket. Okay. Check 0th slot, check to the first slot, then it finds an empty slot and keeps 327 here, and it keeps the position value of where it has kept the key that is mapped to this bucket. You can see that 2 is kept here. Okay. This way, it will fill entire table. Once slot is filled, no more elements can be inserted. Okay. Let's get back to our session. The previous thing, we used different, the previous thing, we used a different bucket. Here what we do is, the keys that are mapping to the same slot, we create a linked list. So if you see here in this example, Tom Smith and Joe, or these both keys are mapping to a key slot of 152. So first John Smith is arrived, so John Smith is kept. The link is created and will keep standard easy. So in this fashion, more and more keys are coming to this slot. All the keys will be chained in a linked list. So this technique is good still, and the number of slots, of linked elements for a slot is less than n by n. N by n. If you have n number of keys and n number of slots, then this chaining technique is better if each slot has a each slot has a linked list. Is number of nodes in the linked list should be less than n by n. Okay. One disadvantage of dealing this is here we are using the linked list. Starting of the section, we said that we want the search thing to be done in big of 1. Here, if you can see that John, if you hash this value, if you want to find John Smith, you can guarantee us that finding the hash key, you will find it directly John Smith. But when you searching for a key like standard E, it needs to search, needs to go to the slot, then it needs to compare sequentially. Okay. So the problem again, the problem results in a complexity of like sequential searching. Okay. Another disadvantage is here we need to deal with pointers. Pointers, so allocating and deallocating of the pointers, which is more complexity consumption thing. So before going to the next technique of resolving the collision, let us look at chaining simulation. How it works. Here you can see that each has two links. Here we can see the link will go on setting it. I think the key that maps to 5 is linked after 216 and first it will get 216 and then got a key value 192, which is 7 gives us 5, which is kept in the linked slot of it. Then go on. Here for triple 5, you can modulus 11, then it is going to again going to the slot 3. So in this way, we will use the linked list for chaining, and each plot, each linked list size should be equal to that of n by m. We have here number of field elements is 1, 2, 3, 4, 5, 6. We have 9 elements. So 9/10 should be less than or less than 0.5. If it is less than 0.5, we can say less than 0.5, then we can say this training technique will work fine. Okay. Let us look at different techniques of open addressing. In open addressing, as we said earlier, we are not going to alter the structure of the table, hash table. So here we have different techniques to solve in open addressing. We will discuss 3 different techniques like linear probing, quadratic probing, and double hashing. Okay. Let us start our discussion with linear probing. What is meant by linear probing? As the name suggests, it will sequentially check for the slots that are available in the table. As the name of linear probing suggests, it will search sequentially for the element. Here you can see in linear probing, first if you will get a key and you will use the hash function h of a with that key, and we'll get the home position where it needs to be mapped. Once this home position is filled, we'll use hk plus 1. The value that we got, hash value that we got, that is the home position plus 1. Then if this slot is also filled, then we'll check for hk plus 2. If this slot is also filled, then we'll search for hk plus 3. These constants which we are adding to search in the list is nothing but probe sequence constant. Okay, you can see these probe sequence constants are only a constant values which are not dependent on the key that we are trying to insert or searching. Okay. Here these probe sequence constants are constant which are not dependent on the value k. Okay. Let's look at an example of linear probing. You have taken a table size of 11 and I have taken a hash function of x mod 11. Now we are trying to insert values like 20, 30, 2, 13, 25, 24, 10, 9. First, I will find a value of, I will find hash value of 20, which maps to the slot 9. So, slot 9 is filled with 20. Hmm. Then I will find a hash value of 30, which is mapped to 8. Okay, I mapped it to 8. Then hash value of 2 has mapped to 2. I position the 2 here. So, for this 2, for the value key 2, here second slot is the home position. Okay. Then if I try to map key 13, I have got a value, got a hash value of 2. So I will go and check my home position 2, which is already filled with a value. So then I will check home value plus probing sequence constant. Here probing sequence constant starts with 1. Okay. So I will use our probing sequence constant and home key value. So 2 plus 1, which maps it to 3. You can see that 13 is mapped to position 3, slot number 3. Then I try to insert a value 25, which resulted me in a hash value of 3. Then hash value of this is the home position for 25, but this home position is already filled with a value that has a collision with a position in slot number 2. So this is filled. So we have a collision. Then what we do is we'll linearly probe for the next slot, that is nothing but 3 plus 1, home position plus 1. So we'll go to fourth slot. Okay. Then if you consider a value of 24, which again maps to home slot of 2. Okay. Here in the first probe sequence, we have taken the constant 1. So it checks the next slot, 2 plus 1, 3, third slot. Then since it is filled, we will check for home slot plus a constant 2. Home slot plus a constant 2. You can see that the slot 4 is already filled. The slot 4 is also filled. Then we will go for the third constant. Home slot plus third constant. Third constant is nothing but 3 here. So 2 plus 3, that is nothing but 5. 5 is an empty slot. So we keep 24 here. Then if you map 10 with key 10, it will go to the slot number 10. Then if you take a value of 9 here again, you take a value of 9, first it maps to 9. 9 is already filled. 9 plus second constant, 9 plus 2, that is nothing but 11, which maps to 0. So 9 is placed here. So if you carefully observe that, values like 13 and 24, which are highlighted in red, their actual home position is slot number 2. But due to collision, has been placed at different slots, and you can see that is all numbers forming a group here, and we have a different empty slot in between the table. So if you are trying more, if you in the worst case, if you are trying to insert more numbers that are mapping to home position 2, the elements are going to linearly search all the slots that are available. So these clusters are going to increase. The worst case. So these clusters are nothing but primary clusters. These are known as primary clusters because all the key values that map to the same home slot are forming a cluster. You can see that 13 and 24 are also mapping to the home slot of 2. So these clusters are the results of key values that are mapping to the same home slot. So this is known as primary clustering. So how do we avoid this primary clustering? Yeah. So we have some disadvantages. Before looking at the disadvantages of linear probing, let us look at linear probing simulation. Linear probing simulation. Here we have one slot for vertex, and we limit our size to table size to 11. Okay. Here is our hash table. Let us execute it step by step and see how it maps. First, it has taken a random value of 86. Taken a hash function of modulo 11 because our size of hash table is 11. We see that the 86 is mapped to the slot 9. Then again, 292 is mapped to slot 7. Then 792 mapped to 0. 474 which mapped to slot 1. 891, 819 is mapped to slot 9. Here, if you can see, 962 is also mapping to the slot 5. Okay, but the slot 5 is already filled, so it will check for the position of the home slot plus 1. Here, home slot is 5, plus 1 is nothing but 6. Once it checks the slot, it finds it is an empty slot. So it keeps 962 in the slot number 6. Okay. You go on. Slot 2 is empty, so it kept 508. You see 280 is again mapping to the position 5. Here position 5 is filled already with 819. So then it will check home slot plus 1, which is nothing but 5 plus 1 6, which is already filled. Then it will check plus 5 plus 2, that is nothing but slot number 7, that is also filled. Then it will check for 5 plus probe constant 3, that is 5 plus 3, that is nothing but 8. Let us see how, since the slot 8 is free, it needs to place 280 in the slot 8. Let us look at it. We checked in the slot 6, it's checking in the slot 7, then it kept the value at position 8 because it found a value at position 8. Okay. You go on. Now, if you look at the table, we can see that there is a cluster of elements here. There is a cluster of elements here. Now, if you try to map a key which is hashing to the position 5, it needs to go linearly through all the elements to the end of the list and again comes to the top of the list, again checks all the things till it finds an empty slot. Okay, just look at it. Now, here is the cluster. So it goes on checking 8, 9, 10. Then it checks for value 0. You can see it is checking value checking the slot 0, then 1, then 2, then it finds an empty slot. So here you can see that it is taking more time because of this probing and due to the clustering of the elements at particular slots in the hash table. These are the disadvantages of the primary clustering. Linear probing. So linear probing has the disadvantages of primary clustering, and it needs to sequentially set all the slots for the empty slot. So the performance is nearly equal to that of the sequential set, which is in the worst case, which is nothing but equal to big of n. Can we avoid this problem of primary clustering? So to avoid this problem of primary clustering, we consider the probing constants that we use for linear probing. Here we use the constants for probing for the empty slots in the hash table. These are nothing but 1, 2. Now in quadratic probing, what we do is for better performance, we use a probing constant sequence like 1 square, 2 square, and 3 square. It is nothing but our home slot plus 1. The home slot, the slot is filled, then home slot plus 4. Then this slot is also filled. We'll go for home slot plus 9. Let us the same example that we have done previously for linear probing. Here also we use the same hash function in the same size of the hash table, and we have taken the same set of keys. Let's map the keys to the hash table. We have taken 20 modulo 11, which maps to the slot number 9. So we have kept 20 here. Okay. Then 30 modulus 11, which is mapping to the position 8. So because these all are empty slots before, so since this is empty, we have kept the value 30 here. Then we map to which is empty, so it's kept here. Then we try to map 13 here, and having its hash value to the home position entered as 2, which is already filled. So we use home position plus instead of 1 in the linear probing, we use 1 square, which is nothing but 1. 2 plus 1, which is nothing but 3. So the 13 element, which is initially mapping to the home slot of 2, is mapped to the slot number 3. Then, if you take a key value as 25 and we try to map it, it maps to the slot number 3, which is already filled with 13. So, we'll use our probe sequence like 3 plus 1 square. Home position slot plus probing sequence constant, we are starting with 1 square. So, 1 square, that is nothing but 4. So, here 25 is mapped to 3, but it is placed in 25. Slot number 4. Is mapped to slot number 3, but linear in quadratic probing in the first sequence, we have mapped it to the slot number 4. And then, if you try to map a value of 24, it is mapping to home slot of 2, which is already filled. In the initial probe sequence, we use 2 plus 1 square, which is nothing but 3. And it will check the slot number 3, which is already filled. So it will go for the second probe sequence constant, that is nothing but 2 square. 2 plus 2 square is nothing but 4. 4 plus 2 is 6. So it will check for the sixth slot. Instead of checking in the immediate slot, it will go for the sixth slot, and if the slot is empty, keep the value here. You can see that 24 is placed in slot number 6. Yeah, then it mapped the 10 value to 10 because 10 is empty. 10 slot is empty, positioned it in 10. Then we are trying to insert a value of 9 here. If you look carefully, you will check for it is mapping to the slot number 9, which is already filled with value 20. So it will check the first probing sequence like 9 plus 1 square, which is nothing but 10. 10 slot is already filled with value 10. So it will go for the second probing sequence. 9 plus 2 square is nothing but 4. This will be equal to 13. Okay. So here, by the end of this thing, slot number 10 is completed. We'll get the 13th slot by getting back to the first slot. So 10, 11, 12, 13. This is the 13th slot. Since 13th slot is also filled, now what we'll do is we'll go for the third probing sequence. 9 plus 3 square is nothing but 9. 9 plus 9 is nothing but 18. So now 18 mod 7 is going to be slot number 7. It goes to the slot number 7 and checks since the slot 7 is empty, we'll keep the value 9. So carefully look at this hash table. Here we have eliminated the primary clustering of values like the previous case we have 22, 13, 25, 24 as a one cluster. But in this case we have just avoided the primary clustering using quadratic probing. But if you carefully look at it, you can see that 24, 29, if you can see these two elements, you consider more set of elements, more and more slots will be accommodated at this position, at this location of the table. First, 24 is placed here because its home slot 2 is already filled. Due to its probing, it came to 6. But the value 9 came here because the slot, its home slot 9 is filled and it's gone through different probes and came here. And if you can see by the color variation, this is formed because different set of values mapping to a different key slot here. In our example, it is 2, and different set of key values 9 and so on mapping here because of different home key. So these clusters are formed because different keys are mapping to different homeland and forming a cluster due to their probing. So this formation of clusters by different keys mapping to different keys mapping to different home slots is nothing but known as secondary clustering. Yeah. Okay. We have seen till now we have seen linear probing and quadratic probing. In linear probing, we have seen the problem of primary clustering and we used quadratic probing and we have eliminated the primary clustering and we have came across a problem of secondary clustering quadratic probing. This is nothing but a definition. Secondary clustering is caused by multiple keys mapped to the same hash key values of different home. These this prolonged mapping of these type of things will result in secondary clustering. So we have avoided the primary clustering and we have faced with a new problem known as secondary clustering. So how do we avoid this secondary clustering? Can we have a better collision resolution technique that we can so that we can avoid this secondary clustering also? So let's look at a better collision resolution. In both, if you consider the linear probing and quadratic probing sequences, what we said is this 1, 2, 3 are probing sequence constant. Here, this is linear probing equation and this is quadratic probing equation. In both the things, here 1, 2, 3 are linear probe sequence constants for linear probing and we used 1 square, 2 square, 3 square are probe sequence constants for quadratic probing. You can clearly see that these constants are not dependent on the value k that we want to insert or set. So if you can make this constant in some way dependent on the value of k, then we can avoid the secondary clustering problem. Okay, in this involving the k in the probe sequence constant is nothing but double hashing. The double hashing, till now we used one hash function to map and use the probing sequence to find the empty slots in the hash table. In double hashing technique, what we do is we'll use a secondary hash function, which is a function of k here, and we use a probing constant like here the probing constant is 1 into p of k, which is a secondary constant, secondary probe constant. 2 into z of k, 3 into z of k. This second hash function plays the main role in double hashing. So here to completely avoid to most of the extent to avoid the secondary clustering, what we do is we need to carefully choose this function so that it is dependent on value k that we are going to insert or set. One way of choosing is we need to choose this function such that h of k should be between 1 and the size the slots of available. The slots are available number of slots. If you have m slots, then your g of k constant should be between this probing constant should be between 1 and m minus 1. So that one your probing constant is greater than or equal to 1 or less than or equal to m minus 1. M is the number of slots you have. Yeah. Till now we have studied three different collision resolution techniques in open addressing. Even then, even From the starting of the session, we have learned that we need to choose a good hash function. Even we choose a good hash function, we came to know that we have problems like collisions and all those things. And we try to solve the collisions by different techniques and like closed addressing and open addressing. Even though we use open addressing collision resolution technique, there might be some problem of collision, which we cannot avoid with this technique. So, what can we do further to mitigate this collision? Before we learn how to resolve these collisions, even after selecting good hash function and all those things, it's a time you need to work on some tasks. Here we have 3 workout sessions. You need to work the first session. You need to work on the first task in the workshop for 20 minutes. Then you need to work on 2 tasks. Are there any doubts regarding the questions that we have given here? Next, we'll look at a topic known as load factor. What's the load factor? Load factor is nothing but the number of, it's the ratio of number of filled slots to that of the total number of slots. Where it is useful and wide and why. Even though you are considering a good hash function and good hash table size, we are not sure that there is no issue of collision. So, our goal of learning this session is searching an big O of 1 complexity. So, if you consider this load factor plays an role in complexity analysis of the hash table. Let us look at load factor and its importance. Load factor complexity of a hash table can be calculated as constant time for hashing and the amount of time that is required to search from the filled hash table. We won't check the empty slots. So the amount of searching will be alpha. So if we consider in our chaining collision resolution, if the table is filled 10 to 10%, that is nothing but 1 plus alpha is 1 by 10%. So that results in 1.1. So similarly, if it is 20%, table is filled 20%, we can see that that results in 1.2. That is, these are the times that is the amount of time that is required to search in the chain. So if the chains are filled to 50%, we can see that it is increasing. That the amount of time that is required to search is going on increasing. When the table size reaches the amount of 90%, then we can see it is nearly equal to 2. So our time complexity of big O of 1, we are considering to have a such complexity of big O of 1. If you want to have big O of 1 in this equation, what the alpha needs to be? Alpha needs to be something which is to be negligible. So it should be like 0.5, 0.3, 0.2. In that case, we can assure that our complexity for searching or insertion will take a time of big O of 1, which is nothing but hashing time. So, if you consider chaining collision resolution algorithm to be a good working enough, so we need to have an alpha value. This alpha value represents nothing but the amount of chains that are linked to each slot should be n by m. So in linear probing, if it is the alpha value is less than 1, we can assure that there is a chance of finding a slot for the insertion, but it gives a reasonable complexity when the amount of size is less than 0.5. We can be sure that we can find a slot if it is less than 1, but it takes some time, time complexity. But if you ensure that the time complexity is less than 0.5 for linear probing, then we can be sure that our search algorithm will not take more than big O of 1. Similarly, quadratic probing also results good when the alpha value is less than 0.5. So, actually, even if you consider this load factor thing, when it reaches certain amount of time, how can we resolve? How can we be sure after crossing this load factor? How can we make sure that the complexity is big O of 1 for searching? To make that possible, we will use a concept known as rehashing. Rehashing is nothing but when the amount of alpha value reaches the value that we have specified here, we consider for a linear probing, if the value reaches 1, then we will create a new hash table which is equal to double the size of the previous hash table, and we will map all the previous keys to the new hash table. So it involves some calculation, and it would involve some time. So rehashing is basically a time consuming problem. So just go through it, and we'll look at other important scenario of deleting an element from a link from a hash table which has some problem. Let us consider the previous example that we have looked for linear probing, quadratic probing. We'll take the same example, and we have mapped all the keys to the table. Let us consider if you are deleting a value of 25, which is mapped to position 24. So we will get an empty slot here. We will get an empty slot here in the fourth slot. So then, if you are trying to search a value for value 24 in the hash table, 24 is mapped to the slot 2. Then it will check for, as 2 is not equal to 24, then it will check for the next slot, 13 not equal to 24. Then it will check for the next slot which is empty. So it won't check for the other slot which is available because this slot is empty. So it will result. The result says that the value 24 doesn't exist in the hash table, which is a false statement. So in order to avoid this situation in for the deletion part, we'll mark this. We'll mark whenever we are deleting a value, we'll mark a flag that it is deleted. Consider this: if you are deleting 25, then we'll mark some flag like true, that it is deleted. Then if you are searching for 24, it will check for the slot 2, and 2 is not equal to 24, 30, then it will check for next slot, 30 not equal to 24. Then it will check for next slot, which is an empty slot. It will check the flag that there used to be some value in this slot. So it will check for the next slot, and it will find the 24. Then it will result that 24 exists in the table at certain position. So this we'll mark like this. We will mark different elements that are deleted, and at some point we'll rearrange all the elements and we'll remove the flagged elements. We'll delete the flagged elements. So this flagging and removing deleting the elements at certain point after certain adjustments of the table is nothing but lazy deletion. So if you go through the concept of lazy deletion, you'll find more examples over the net. Actually, the concept of lazy deletion is nothing but marking the slot which is deleted, and we'll delete all the elements after some adjustment so that we won't miss the values that are already exist in the table. Okay, this ends the session of hash table. We'll continue with the session with trees now. We'll discuss the session tree on trees. Let's continue with the session trees. So we have seen till now we have seen many data structures like which allows faster search. But if you consider hash table, it has certain limitations like load factor and selection of hash function and all those things. We are losing some flexibility there. We are when the set when the key set is becoming more and more, then we are having some problems with the operations. So in the sorted tables, we have seen that it takes big O of n time for search, and it takes big O of n for insertion and deletion. Similarly, in the hash tables also, worst case, when the load factor is nearly equal to 1, then we are having a problem with insertion and all the functions. So operations. So how can we eliminate these limitations when the key set is really big? So we'll study in this session trees, which can address all these issues. And there is no need here, like in the hash table, we need to define a table size in advance. So in trees, there is no requirement of redefining the size of our data structure. So how can we get this? How can we get this flexibility? Let us look at how can we get this. So in our early sessions, we have seen that linked list, when we consider a linked list which is unordered, we can see that we can insert and delete the element with a complexity of big O of n. But we can see that we need to set the entire list in the worst case for the element if it exists or not. And we also again studied another algorithm of binary search, which gives better searching complexity like log of big O of log n. So insertion and deletion are better in case of unordered linked list, and searching is better in binary search. But one limitation in binary search is we need to have the list to be ordered. So by combining these two ideas, the linked list idea and the searching of certain part of the keys that are available, is nothing but combining these two ideas will come across the idea of trees, where we have the flexibility of linked list of inserting and deleting in big O of n, and searching of a certain number of set of keys among all the set of keys, like binary set. So let us look at what are formally we look at what are trees. A tree is nothing but a special data structure which has a special node known as root, and it have different childs, and each child is again recursively a tree. This tree, if you consider, can have any number of childs. So we'll come across a concept like k-array tree. So then a k-array tree is nothing but a tree which has an k number of childs, while each child is also recursively a k tree. Okay? If you consider a binary tree is also a special case of a k tree, which has a k value that is equal to 2. So why do we study most of the times when we are studying data structures, we'll consider only the binary trees. Why do we study only the binary trees? And Why not K trees? Okay. Here we need to keep in mind that any data structures that we are using will store the entire data. The data that we store in the entire in the data structure will reside in the main memory of our computer. So it is reasonable to use a limited amount of space to store the data in the primary memory. So if you consider the K array tree, if you look at this K array tree, which has three nodes, it's nothing but uh, three array tree. So if you consider a three array tree, if you have considered 13 nodes in a K array tree, three array tree, we'll have 39 number of pointers because we have 13 nodes. Each node will have a 3 childs. So 13 into 3 will result in 39 pointers, 39 pointers. So we have a calculation like, so in any case of arrangement of these 13 nodes in a K array tree, we'll have a formula for null pointers like n into k minus 1 of plus 1. If you look at this, n is 13 here and k minus 1 will be equal to, here k is 3. So k minus 1 is 3. 13 into 3, 13 into 2, which is 26, plus 1 is nothing but the number of null pointers. If you are not sure about the formula, let us count the number of null nodes here. In the first level, it has 3 childs. So there is no null node. The second level, we have 3 childs. So no null node. We have 2 null nodes because one node is useful here. So 1, similarly for D, 1, 2 plus 1, 3. In this case, we have 3 null nodes, 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 3, 3, 3. So how many we are having? 1, 2, 3, 4, 5, 6, 7, 8. 8 into 3 because each child should have 3 nodes. So 8 into 3, which is nothing but 24 null nodes for the leaves, and in the previous case we have 3 null nodes. So 24 plus 3, that is nothing but equal to 27 nodes. So we can see that useful slots is 12. 39 minus 12, 27, nothing but 12. Or we can count it here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Out of the 39 null nodes, 39 total number of pointers, we are using 27, we are using 12 nodes only. And we are creating 27 null nodes which are not useful, and these 27 nodes in the main memory, they are taking certain amount of space which is not useful, but we are allocating the memory. So it is wastage of, it results in the wastage of space. And one more important thing is, any tree, any K array tree can be easily represented as a binary tree. So it is useful to study binary tree. Let us look how do we map a K tree. Let us consider our previous K array tree and look at how do we map it to a binary tree. Let us take the first root node as it is as a root. Then we will map the first child to its left. That is nothing but B, which is mapped to the left. And we will map all the remaining childs to B by moving to the right pointer. If you see, after mapping B, we can map C and D to its right pointer Similarly, A is, we have to map B. B's first child is E. So we will map E to the left node of it. Then we will map the remaining childs F and Z to E's right node. By recursively doing this, we can see that our K array tree is mapped to a binary tree which has a root at A and every node will have a 2 nodes. In this case, if we consider our previous analogy of number of nodes, as here we have total number of 13 nodes, and we can see that as we reduced 3 childs to 2 childs, here it becomes 13 to 26. Total number of pointers is 26. So, out of 26 pointers, the number of null pointers will be equal to 26 into 1, that is 2 minus 1. 26 into 1 plus 1, that is equal to 26 is the number of nodes, 13 into k minus 1 is 1. So 13 into 1, that is nothing but 0.14 null node. That is the formula. You can also check it here. Here we can see that we have a null node in the first level. We doesn't have any null nodes. We have a null node here, 2 null nodes. Now no null node, 3, 4, 5. Here we have null node 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 14 null nodes. So out of 26 pointers that we have created in the main memory, we have used 12 pointers, and this 14 pointers also created, but we can't avoid this because we by constructing the binary tree in any way, we will have a certain number of leaves. So these leaves will not be having any children. So it will result in 14. So we can't avoid this. So at certain point, depth of learning the trees we can avoid by using the balanced tree. We'll look at it later. Let us continue. So by this slide, we are clear that we can create a binary tree from any k tree, and we are clear that why do we learn binary trees when we have k trees and other, because k trees and other trees use more memory in the main memory. It is better to have study binary tree, which reduces the number of slots, which reduces the number of null pointers. So let us look at some terminology that is associated with binary tree. So every tree, we can consider this terminology for every tree, but if you look at, we are looking at binary trees, we can see that the nodes that doesn't have any child, that are known as leaves, and every except the root, every node will be having a parent. If you see that D, E, F are the childs of B. So here D, E, F are nothing but siblings because they are children of same parent. So if we consider I, J, K are the descendants because this ancestor of these things. You can see that B is the ancestor of I, J, K, and F and the parent of the child. So these are some terminology which is used, and depth. You can see the depth and the levels. Height of the tree is nothing but 1 plus maximum height of the left subtree. You can see if it is if you want to have a size of a tree, you can consider 1 plus maximum height of the left subtree and the right subtree. Here the left subtree is this thing and the right subtree is this thing. So continuing, we will come across some of the types of binary trees like full binary tree, complete binary tree, and balanced tree. What is meant by full binary tree? A full binary tree is one which has all the nodes except the leaves Accept the leaves. If you consider this thing, accept the leaf, all the nodes will have complete set of children. In a binary tree, the complete set of children is 2. Accept the leaf, you can see that the parent has 2 nodes. Here also you accept the leaf, you can see that these nodes have 2 children, this node has 2 children, this node has 2 children. This is full binary tree. When you consider when you are looking at complete binary tree, in the complete binary tree, accept the last level before the level before the last level will be filled. Filled in the sense it will be having uh, all the children. Consider this tree. You can see that this level at this level, its parent has 2 children. So at this, if you consider this as a, see that this has 2 children. So this also has having the 2 children. Here we can see that at the leaf node stage, at the last level, the elements are filled from left to right. In this case, this is filled. Here it is filled. You can't have an array. You can't have a complete binary tree such that one element is filled and this is not filled and you can fill this element. So this is the condition that at the last level in the complete binary tree, at the last level, elements should be filled from left to right, and the level before the last level should be completely filled. So, every complete binary tree is a full binary tree, but every full binary tree can be a complete binary tree, but every complete binary tree cannot be a full binary tree because in this, if you consider this as a full binary tree, you can see that this node is not having the second child as it is a binary tree. To be uh, this tree to be a full binary tree, you need to have a second child for this node. You can see this is a full binary tree, but also complete binary tree. Yeah. So here you can see that every full binary tree can be a complete binary tree, and every complete binary tree cannot be a may or may not be a full binary tree. So what is balanced trees? Balanced trees is nothing but if you consider the left subtree and the right subtree of a node, the the difference of the height should not be less than or equal to 1. So you can have see here for this node, the left subtree has 1 node, and for this thing right subtree has 0 node. So the difference is 1. So this is a balanced tree. If you consider this node, this has you can see that it has 1 child, it has 0 child, it has 0 child. So you can have you can see that the difference is 0. So this is a balanced tree. So for binary, so for a tree to be balanced tree, it should have a height difference in the left subtree and the right subtree. Height difference should be less than or equal to 1. Now, how can a tree represented? Trees can be represented using a array or a linked list. So let us consider this what we have seen here examples. This is a skewed tree, left skewed tree, where we can see that in the worst case, all the elements are mapping to the left of the nodes. Root, here node root is A, and B is mapped to its left. Then C is mapped to its left. This is the worst case scenario. No, this is nothing but this is as skewed left tree. We have a example of somewhat better binary tree. So if you try to map these two trees to an array, so here if you are trying to map these trees to arrays, there is a relation between a parent and a child. If the parent is at position I, then its left child will be at 2i, and right child will be at 2i plus 1. So first we'll consider the left skewed tree, and we'll try to map this to an array. If you look at the array, if you are taking root position as 1 and mapped the A to 1, then what is the left? B is at its left side. So what is the value that B should go? 2 of I. I is nothing but 1 here. So 2 of I is nothing but 2. 2 into 1 is 2. So B is mapped to 2. C is left child of B. So it should map to 2I. So 2 into I is nothing but, for B, I is nothing but 2. 2 into 2, that is nothing but 4. If you consider C, which is, if you consider D, which is mapped to left child of C, then it should map to 2I. What is 2I? 2 into I mapping to 4. 2 into 4, that is nothing but 8. So here E is mapped to left child of D. Then we will check 2I. 2I is nothing but, I is nothing but 8 for D. So 2 into 8, that is nothing but 16. You can see that most, when you take an array size of 16, 17, you can see that there are empty slots while mapping this left skewed worst case map array tree to the array. So if you consider the same type of mapping 2I and 2I plus 1 for this tree, you can see that B is mapped to left child of A. A is at position 1. So 2I is at position 2. 2I is at position 2. So B is mapped to 2. C is, what is the position of C? It is mapped to right tree, right pointer of the A. So it will be at 2I plus 1. 2I is nothing but 1 here. 2I is 2 plus 1 is 3. So C is mapped to B. In similar case of mapping, we can see that for a complete binary tree, we can see that there are no wastage of memory in the array. And consider here, we are taking less number of array. So less number of arrays slots. So we are sure that if it is a complete binary tree, it is better to use a array structure. What if what if our tree is in worst case, or in most of the real world scenarios, we are not sure that our tree will be a complete binary tree. So we'll study a different way of implementing the tree. So we'll study a different way of implementing the tree, that is nothing but using a linked list. Here we'll create a node. The nodes will be like this. You can see here. The node value will be in the element space, and the element should be pointed in the left pointer, and right element should be pointed in the right pointer. So considering the previous complete binary tree, we can see that the linked list representation over here, it shows how it is mapped. B is mapped to left child of node A, and C is mapped to right child of node A. Similarly, if we consider the worst case tree, which is Q tree, we can see that using 5 pointers, using 5 nodes, we can just map A, B, C, D, E, F, G, A, B, C, D, E, F, E using the linked list. So by using the linked list, we are removing some space which is wasted in the last case of representing it in array. But we are not sure of, if you are basically considering this linked list will have an overhead of maintaining this pointer and space required to allocate this memory dynamically. So keeping in limitations in both the cases, we need to select our representation of the tree based on our data. So first we need to analyze our data, then we need to come up with whatever the representation that we want to used for representing a binary tree. Next, we'll learn about the concept known as binary search tree. Till now, we have seen that trees, binary trees, which doesn't follow any order. So here B or C has no relation with with its parent. So you can see that you can have C here, B here, anything. So these relation there are no conditions for the elements that are based on its parent. So childs can be kept in any order. So one limitation in binary search tree is we need to have keys that are present in the left subtree. Left child will compulsory should be less than or equal to the its parent. Let us consider a simple example of numbers here, natural numbers here. First, we fixed our root as 21. Then we came across value 3. 3 is less, so it should be in the left child. So we mapped the 3. Then we came across a number that is 34, which is greater than 21. So 31 will be compared with 21, and it will map as it is greater than 21. It goes to the right child. Then we'll get a value 2. Since 2 is less than 21, it will go for left. 3 is less than, it is left. 2 is less than 3, then it will go for left and it will place the 2. Similar type of arrangement can be also used for the string comparison, alphabetical comparison. So let us look at some operations on tree, like insertion. Here, if you have consider you have it like this, and you want to insert a value 36, every while in process of insertion, we need to check. We should start from root node and to check compare the given key with the root node, and based on the result, we need to navigate through the tree. In this example, let us consider if you want to insert a value 36. First, it will check with 36 will check with 30. As 36 is greater than 30, it will move on to this. Here, 50 is greater than 36. So you should move left. So it will move left. Here, 35 is less than 30, 35 is less than 36. So you should move right, and you should place your new element here, which is nothing but 36. So you can see the insertion column. Similarly, if you try to delete an element from the tree, binary search tree, we have 3 scenarios. First, we will consider the basic scenario of removing element if the element is a leaf node. Leaf node is nothing but the node which doesn't have any other child. So, if you consider here, consider in this tree scenario, if you want to remove the value 36, so first we need to find out the position of that. So we'll go through it. 35 is compared with 30, as it is greater than 30, it will move to the right, and it compares with 50, as it is less than this thing, we will move to the left point, through the left pointer to the next position. Then we will find this 35 equal to 35. So we will place a null in the left pointer of the 50, and we will remove this element, which is nothing but this. In the next case 2, consider if the element that you want to remove has a single child. In this case, if you take the previous example, if I want to remove a value of 10 from this tree, first I need to find it, and I need to place whatever the links that existing with that deleting node to the previous to its parent. Let us look at it. If you compare to delete a value 10 from it, 10 will be compared with 30 as it is less, it moves to the left pointer. So 10 is compared with 20, it is less because it will, so it will move to left. Then it will compare 10 with the 10, and here you can see that there is a node that is pointed to the node, that is node 10 to its left pointer. So before removing this, we need to take this value and we need to point, we need to go to its parent and point its left pointer to the left pointer of the deleted node. So here the 10 is deleted, and the value that is pointing left to the 10 will be now pointed to the left pointer of 20. Okay. If you are clear with it, we will go on to the case 3, where if you want to remove a node which has both the childs. In the case 1, we have seen the element with no child, that is removing an element with no child, that is nothing but leaf. And in the first case 1, we have removed the element with a single child. In the case 3, we will look at an removing element which has both the child. In this case, we have two opportunities to replace the deleted element. Here, if you want to remove element 20, consider this 3. If you want to remove an element 20, one thing we can do is replace the minimum from the right subtree. We need to find out the minimum of this 20, minimum from the right subtree, or we need to get the maximum value of the left subtree. Okay, in the first case, we can see that replacing with the minimum element from the right subtree. So to get the minimum from the right subtree, we'll while deleting 20, we'll compare it with 30 and we'll come here. And while before removing it, we need to find the minimum of this minimum from the right subtree. So the minimum of the right subtree will be there when we move one step right, and we'll move left until we get until we get to the left node, until we get to the leaf node. Here I want to delete 20. So I will go one step right, and I will move through the left pointers until I reach the leaf node. So here I moved right 25, then I am moving left. As I doesn't have any other nodes here, and I reach the last level, I replace this 22 with the element that I want to delete. So here you can see that it is 22. If you check here, if you check this tree, you can see that it is still following the binary search tree principles. That 22 is greater than left subchild, and 22 is less than its right subchild. In this scenario, if you want to get the maximum from the right subchild, you will navigate one step to the left, and it doesn't have any other right nodes. We'll just remove this thing and we'll place the 10 node here. In this case also, if you check it, you can see that 10 replaced 20, and 10 is greater than its left subchild and less than its right subchild, which is nothing but 25. If you are clear with these deletions, let us look at the animation of binary tree. EST. If you look at this, this is an animation of binary search tree. We'll first construct a random tree. Okay. will construct a random tree, and if you want to delete certain element, like if you want to delete a leaf node here, if I have a leaf node like 5, so I will enter delete 5. If 5 is a leaf node, I want to delete it. So it will check with node, root node, then it will move, since 5 is less, it will move left, since 5 is less, moves left, is less, moves left, again moves left. It finds the node, so it is green. It finds the node that needs to be deleted, so it will delete. So there is no problem with the case 1. Now, let us consider with case 2, which has a single child. Here we can see 10 having the single child, it is nothing but 12, right child. So, what we need to do by deleting 10 is we need to keep this right child of 10 to its parent's right child. Let us check how it happens. Now, if I click delete, it will check for the compares with the road, less it goes to the left, less it goes to the left, goes to the left, goes left, and it finds the element that to be deleted, and it will remove it and it places the child to it, right child to it. As the tree square is not able to adjust it, so it will be a left. So since 10 is the left child of it, you consider the previous scenario, 10 is the left child of it, so 12 will be replaced as the left child of 53. Now let us consider removing the element which have both the left subtree and the left subchild, left tree and left child and the right child. Here 61 has both left child and right child. Let us see which scenario it follows. C1. I want to delete it. We will compare with the node, less, compare, less, then it finds it. Now it moves one step to the right. You can see it moves one step to the right, and it moves left until it finds until its left node is null. You check it, it moves to 64. Since its left node is null, it will 61 will be replaced with 64. You can see 61 is replacing the 61 will be replaced with 64. If you consider, if you check this tree, you can see that it is still following the principles of binary search tree. Here 64 is greater than its left subtree and 64 is less than its right subtree. So in this animation we have seen that it moved to the right and it moves one step to the right and moves left until it finds a null node. Let us 3 again. 39 has both the nodes, so it will check with the root. Less, 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 less. It moves to the left. Now it goes to the right and checks if it has any left element. If it doesn't have any left element, it just replaces it. So it gone to the right and no left node. So it is trying to replace with 39 is replaced with 44. You check the this tree, you see that 44 is greater than left subtree and right subtree is null. Here we can say it is following the binary search principle. So now we look at binary search tree traversals. So here, if you go to the traversals, you can see that in a traversal, every node in a tree traversal, you can see that every node is touched 3 times. If you consider this, every node will be touched 3 times. So, see how it will touch is once it will touch from the left, once it will touch from the underneath, and the last one is from the right side. You can see A is touched here left side, B also left side, D also left side, D touched here second time for the underneath, and third time for the D from the right side, B second from the underneath. You can see E also 3 times here itself, left, underneath, and right. Here, B is touched third time for the right, from the right. In this manner, every node is touched thrice. Once from the left side, second from the underneath, and the right, third from the underneath. We'll look at 3 different traversals of tree: in order traversal, and in order traversal, pre-order traversal, and post-order traversal. How these traversals are differ? This is informal discussion. This cannot be coded, and just for the sake of idea, how we can represent, how we can, by seeing a tree, how we can write the traversal. So, in order traversal, every node is printed. Every node is printed when it is touching from the underneath. Yeah. Let us consider this tree. Hearing stop nahi kar raha. Okay. If you consider this tree, we can see that here by traversing, A is touched from the left, so it won't print. B is touched from the left, it won't print. C is touched from the left, so it won't print. Then the D is touched from underneath. You can see D is printed. Again, D is touched from the D. We can see that the traversal is touching the D from the right side, but it won't. Then it will go for B from the underneath. It will touch for B underneath. You can see B is printed. Then it will go. It will touch the E from the left side. It won't print. When it touches from beneath, underneath, you will see that E is printed. In the similar play, in this fashion, we can say that how the tree is printed in order traversal informally without doing any code. Similarly, we can see other traversals in post order. In post order, the element is printed when it is touched from the left. You can see while the traversing, A is touched from the left, so A printed first. Then B is printed from touched left second, so B is printed second. So here D is touched left from for the first time, so D is printed. Then again underneath B, it is touched left, so E is printed. In a similar fashion, we can say post order traversal, pre-order traversal without by looking at the tree and without doing anything. Similarly, post order, here the printing is done when it is touched on the right side. Here you can see it traverses left from A, traverses left from B, traverses left from D, underneath the D, and touch right of D, then D is printed. Underneath the B, it traverses underneath the B, left of E, beneath, underneath E, then right of E, then E is printed. A is traversed underneath. So, by traversing this way, you can see that by the end of the traversal, A is traversed the last from the right. So, A is printed at the last. So, this is the informal way of discussion how the tree is printed when it is traversed in order, pre-order, and post-order traversals. But we can't write a code like this. So let us look at the codes, how it is implemented. The pre-order traversal, in the in-order traversal. Let us consider an expression tree. Here, you can see that in the in-order traversal, root is printed first. root is nothing but A. Here it is, sorry, in order traversal, the root is printed when all the left subchilds have been completed. This is the recursive code of in order traversal. Here, we will pass the root plus to the recursive call of to the in order function. Then it will check root is null or root is null. Since the root is not null, then it will move. Then it will execute this line. In this thing, we are calling again, recursively calling again in order function by passing a value of this local root as left child, that is nothing but star. In the second case, it will check star equal to null. So, in this fashion, it will move till A is passed here. When A comes here, it will check A is not equal to null. Then it will go into it in order of left child. Since in order of left child is null, it will go to its previous execution and it will print the value. So it is printing A in this stage. So first in the in order traversal, it will traverse left, 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 left until it finds a null. Once it finds the null, it gets back to its previous stack, its previous call in the recursion and prints the root. Then it will check for once it printed the root, it will again recursively call its right child. So it will check for the right child. Since the right child is null, it will go to again to its previous call. Previous call is at slash. So slash completed its left subtree. So since it completed its left subtree, it will print the root node. Since it completed its left subtree part, it will print the slash. Then it will go for the right side, right in this. Then it will go for its right child. Once it goes to right child, it will check for the left child of this thing. It's calling with B. B will come here. Check B is not equal to null. Then again it will call B of its left child. So it will check B's left child. Once it is called, it finds the null node and comes back to its previous call stack. Then once it comes to previous call stack, it will be here. So B is printed. Then it will call the right subchild. So since it passes null to the local root, it will check null. So when it comes out of loop and gets back to the previous call where it has come from. So previous call is from slash. So it checks the right tree. In the previous call, we printed the slash, and also completed the right subtree. Our control will be here. So this call is completed. So it will go back to its previous call. That is nothing but left call of the star. Similar fashion, it will print entire tree. You can just copy paste this code and you can check the tree, the traversal of and printing of this code. For your better understanding, you can print the positions of these things so that you can clearly understand where call stack we can clearly get the positions where positions of the execution in the call stack. Okay. Similarly, for the post order condition, the root node is printed at the last. We are displaying the node at the last. Once we traverse the left subtree and the right subtree of the node, then the local node's right subtree is printed. Okay. For this understanding, I will just give a view of first few cases. Here also we pass the root plus, then it will go for its left child, then it will again call its left child, then it will call its again left child. Here in this case A is not equal to null, again then it will call its next child. So in the next child it is null. So it will come to the previous call stack of A, which will be here, because we gone left from this and found null and came back. So we will our control will be in the next stack method positioning, we will be here. So then it will pass the right subchild, which is nothing but null. So it checks with the null and comes back. So our in the previous call stack will our condition will be after this statement, which is nothing but printing of the local node. So the printing of the local node is nothing but A. So we printed A. So in this case, we have completed entire these three statements. So in this call stack, there is no statements to execute. So it goes to its previous call stack. So in the previous call stack, our uh, our execution will stay here, because our execution will stay here and our pointer will be here. So here we called, at this pointer we called the left child. So we went to A. So our left child is completed. So now we have to go for the right child. So it will check B. Then this statement is executed. So in the similar case, if you can analyze it, you can get a better idea. So we'll carry on with the discussion with pre-order. In the pre-order, the element is the node is printed first. The root is printed first. So if you look at this thing, we pass our root as plus. It will check if the root is null. Since plus is not equal to null, just we'll come to the first statement execution, which is nothing but printing of the node. So it prints plus. Once it done the printing of the node, then it will go for pre-order, recursive call of pre-order of the printed node's left child. So it goes for the left of the thing, and it will call a pre-order on this thing. If it calls a pre-order on this thing, it will pass a local root as star. Then star will be checked against the null. Since it is not null, what it will do is it prints the star, and it goes for the next statement, and it will call for the recursively call for the pre-order for its left child. So it will move to next. So in this case, it also prints the star and it moves the left. Then it also moves the prints the thing and it moves to left. Prints the root and moves to left. Since it has a null condition here, it comes back to its previous call stack. So in the previous stack, it has printed A, and the call stack will be at here, because it completed its left child. In the printed A, and it checked its left pointer as null and came back. So the pointer will be here. So in this case, it checks the right child, A's right child. So A's right child is nothing but null. So it goes to the previous call stack. So it comes to here, and for this thing, it has printed it, and it has done with the left part, because we have printed already all the nodes and all the nodes of A. So we have done this thing. So it comes to the third case. So in this case, we will pass a local root of B. So B will be passed. B will be checked against null, and if it is, since it is not null, it will print the B. And again, recursively, it will call for its left child and right subchild. Since both are null, it will go to its previous session. Then, for this pointer stack call, we have done with the left child and the right subchild. So, we will go to previous call stack. In the previous call stack, we have done with star, and its left child is already, left subtree is already completed. Then we will go for the right subchild. In this fashion, we can print the post order traversal. Okay. Now, just we'll look at a traversal scenario simulation. Okay, if you consider retraversal, here in the previous section we have in the section 1 we have explained how to build a expression tree. If you consider this expression tree, you want to check, here is the expression that I have given, and this is the expression tree that has been. If you want to check, if you want to get the same equation, you need to traverse in orderly. Here we will check the in order traversal. It is calling and pushing all the in order sequences to it. This is a call stack. Oh, is somewhat faster. Actually, it is keeping it. You can see again order. First, it will call in order on the root. That is nothing but minus. So it pushes a method stack into the stack. Method into the stack. Then here it will check minus equal to null or not. Then if it is not null, then it will for its left child. And it recursively call for its left child. Here left child is plus. So it will call in order of plus. So in order of plus, when it calls in order of plus, you can see that in order of plus is called and it is pushed into the method stack. Okay. Once it is pushed into the method stack, it will come plus is compared against the null. Since it is not equal to null, it has to move to its left child. Here the left child is nothing but division. So it will call its next method, a recursive method with a slash as a local root. Then it will push a method into the stack, okay, in order of slash. This method is called. So we are here. So then we will go on. Then it will compare slash against null and slash against null, and it will go to its left child, that is nothing but in order of 8. So it pushed the method into the call stack. So then it will call, it will check for its next null, next left child, and as the next, it will pass a null as its next local root. Since null is equal to null, it will come to its previous case, which is nothing but in order of 8. In order of 8, and here in order of 8, then it will go on printing the 8. You can see that 8 is printed. Okay. The call stack is it? The call stack is a method in order of 8. So it printed. Once it printed the local node, you can see that there is an in order call on its right child. Okay. Here, in order call of its right child is null because it doesn't have any right child, right child. So it will pass a null. So it passed a null and returned back. So it passed a null and checked it. Since it is null, this condition also done. So at this condition, every node is checked, every statement is checked, every condition is checked. So it comes back to its previous call. That is nothing but slash. It has done its left portion. So it prints its local child. So its local root is slash in this case. If you observe this call stack, its local child is slash. So it prints its local child, and then it needs to call its right child. Right child is nothing but in order of 4. So we'll need to call in order of 4, and we need to push it into the method start. Let's look at it how it happens. See, it went to its it called its right child. So since it called its right child, it has kept a method call of in order 4. You can see it. So once right child is pushed into it, it checks with its left child. Since left child is null, it gets back to it. It checks with right child is null, so it get back to it. So once it get back to it, it will go, when the call stack is done with the right part of this thing, it will go to its previous call, that is nothing but in order of slash. So it went to its previous call stack. Its left child is completed, its right child is completed. And since it's completed its left child and its right child, it will go to its previous call, that is nothing but in order of plus. So it will go to its right child, that is plus, and after right child is it went to its previous call set. It sees that left child is completed, then it should call on the right child. So in order of 6 will be called. So in order of 6 will be it's called and already printed. So the animation is a bit faster. So you can, in this order, you can see that every node is, you can, if you observe this animation, this also, this animation will also be updated on the portal, and you can clearly see the call stack and how it is done. Now we have seen that in order expression, what we have given is, and what we have got are equal. It says that our functionality is correct. If we can, in the similar way, we can traverse the tree in the pre-order. You can see that this is the pre-order of the given expression tree. Similarly, we can do it the post order on the given tree. One thing, one thing is you need to carefully go through each step, and you need to check what are the function calls and what are the pointers that are and what are the positions that it is stopping to recognize what are the next calls that it is making. This is the post order traversal of the given tree. Yeah. So we have some problem set based on the topics that we have discussed. Better if you do these tasks by next session, and we'll keep all the videos and the animations for this session on and the previous session video by tomorrow. And I just give a brief of the questions. What are the problem set that we given here? You see that you have you need to write a program that takes an equation like this. This is an example of example equation, and you should result in a tree which is shown here. Here you need to use stack and the method calls that I have discussed previously, and you need to write the code in Java. This is the first question, and once you have built the tree, use the same tree, and the codes that we have discussed for the pre-order, in-order, and post-order traversal, use the recursive code to print the expression tree that you have done in the problem set 1. Okay. Then question number 3, here your program needs to take 2 strings, use the first string and use individual characters from the first string and build a binary search tree from the characters of the first string. Then use the second string and the characters that are present in the second string, delete the characters that are present delete the characters from the tree that are matching with the characters in the second string. Okay, I'll repeat it. Once you form the tree with the first string character with the characters of the first string, you need to remove the characters from the tree which are matched from the second string. So in then you need to print the remaining characters that are present in the tree. Okay, if you are not clear with the question, you can uh, ask. You can ask in the chat box. So before ending our session, as we said that we will discuss about real world application of hash table, that is nothing but symbol table. We'll look at the animation, how the symbol table works, and you need to work on this project by the end of the next week. So let us look at the symbol table, how it works. See, if you can see here, we have certain conditions. You can read. You can read the conditions. We'll upload this animation on the portal. For simplicity, I'll just read out the declarations if you are unable to see it. Here, we'll write a code in this code input part, and once you done with the code, just press the tab. This area, you can see that if your code has any errors or not. If your code doesn't have any errors, the pointer will move to a array m, and you need to give random inputs, random numbers in the m array. I will explain how this m array is useful while constructing the symbol table. And we need to then once you're done with giving the different numbers, random numbers with m, then you need to give the size of the table, hash table in P. Let us look at the working of the animation. If I type a code like integer variable I, semicolon, every line should end with a semicolon, my code, and I will write a variable float I. If I try to execute it, like if I try to press tab on it, here you can see that the variable I is declared in the same scope. Here, if you consider this as a scope 1, you consider this as a scope 1. You see, int I, float I, both are variables I declared in the same scope with the same variable name. So it is giving an error that it is in the I is redeclared in the same scope. If you consider a programming language or IDE, we can get that there is a duplicate variable declared error. Okay, so if I want to define a different scope for float I variable, what I do is just I will use the parentheses. So now this I is in the outer scope, and this float I scope is in the scope inside the braces. So if I try to execute by pressing a tab, I see there are no errors. So my pointer went to here. So I will give a random value for my M array 1. Here I will give 1, 2, 3, 4, 5, 6, 7, 8. Why, why I am giving these many values? We'll look at it later. Right now, we have given different values for the random values for the array M. And for the table size, I have given it as 8. Let us execute it. You can see here, it formed a table with a hash table of size P, which is nothing but 8. So we have 8 slots, and we are using a function of sum of mi. I is nothing but the index. Okay. V is nothing but the variables array. Okay. Here you can see that the code line int I is highlighted. So I am taking the variable I and I am keeping it in variable array. Now, if you can see it at index I, so our variable is at index 0. Okay. So only our variable length is only 1. So we will consider only M0 and V0. Modulus of P is nothing but the table size. Okay. Let us look at it. Here, if I consider I's ASCII value as 105, I's ASCII value is 105, I am taking a ASCII value of V of, here order is reversed, but V of I is 105, M of I is M of 0, which is nothing but we have given as 1. So 105 into 1 modulus 8, which resulted in hash value of 1. So it should map to the position 1 in the hash table, the variable that we have declared, type of variable that we have declared, the scope. Scope is 0. It is declared outside, so the scope is 0. Now let us go to the scope of what it will. Let us uh, look at float variable I that we have declared. Okay, our code will go to float I. The I is placed in variable section, variable array, and again it needs to calculate. Here it will take, here variable is I, which is same as the previous case. So we got the same ASCII value as 105, and the variable is at the position 1, 0. So we will take the same m of 0, which is nothing but 1. So here it is mapping again to the same hash value. So we'll look at what it happens. Here you can see that I is mapped to the same index with I is mapped to the same index, and variable type is of type float, and you can see here that it is in the scope 1. That is why we are not getting the error. So if it is in the scope 0, then we will get an error of duplicate array declaration. Yeah. Let us now look at why we are declaring the length of, we are taking the array size, we are taking n array with different array size. Okay. Let us consider same, let us consider same. Consider the same scenario, and if I given an input like int aim is the variable that I have declared. Okay. In the initial case that we declared a variable of variable I, which is of size 1. Now we are declaring a size 3, which is Kim. Yeah. Now I declare a float variable with the same value FL. So I will declare it Kim again here. What it will do is, first thing it will check for the error, no error. Then it will ask for me the random values for the table calculation. So I will give it 1, 2, 3, 4, 5, 6, 7, and the table size I will give it as 8. Then you can see here that Here, as we done in the previous case, it has created a table of a hash table of size 8, and we are using the same formula. Here we will look at the importance of this random numbers and the summation. Okay. Here, if you can see it, here the line with int int is highlighted. So it will place the Kim as V of 0k, V of 1 as I, V of 2 as M. So you can see that Kim is placed as K in one slot, I in one slot, M in one slot. So now if you go on calculation, you can see that it will take K's ASCII value 107, M's 0th index 1. Since it is a sigma, we will add plus, then I's ASCII value is 105. Okay, then it is at the M second position, right? We have a value of, we have given a value of 2. So 105 into 2, M's ASCII value is 109, and its M's third position is 3. So we'll multiply by 3. As we have sigma, we'll add on all these things, which and divide it with the size of 8. So we'll get a slot of 4. So if you run it, you can see that it is mapped to 4 Kim with an integer type and scope 0. Similarly, Kim with float type and scope 1 is mapped to the hash table. This is the basic idea of how the hash table works. You need to implement this project using a console based thing